It's a beautiful evening. You're all welcome to tonight's class. How was your day? Hope you are doing great. Oh, okay. So, guys, welcome. You are powerfully welcome to tonight's class. I believe you guys enjoyed yourself today. I'm sure you enjoyed your day. So, we have quite a number of things to get into. So, we'll be starting the class immediately. So, in our last class, we went on to talk about, we started from the general theory of probability. We highlighted the formula for probability, and I'm sure you guys can recollect. We said probability of an event is the number of elements of the event space over the number of elements of the sample space. And I define the sample space as the total number of possible outcomes in an experiment. All right. I went on to identify different sample spaces. We considered several events, several experiments, and we went on to derive sample spaces, event spaces, and we also proceeded to go on finding their respective probability. We also talked about playing cards, and I told you the constituents of a playing card, a pack of playing card, and you went on to solve several questions around cards. Also, we decided to delve into the first aspect being the union of events. And that was under the general subtopic of combination of events. And then we also talked about the intersection of events. All right. And I also defined to you guys what independent events were. We talked about independent events. All right. And finally, for the night, we went on to talk about mutually exclusive events. All right. Now, this is where we stopped the last class. And if we have enough time, we'll continue from here. But before we come back to this, because I believe I already gave you the understanding of mutually exclusive events, I want us to quickly dive into another subtopic on our probability, and that is conditional probability. It's a very examinable aspect of probability, although very simple, but it gives examiners the opportunity to be technical because it has to do with lots of word problem, and any student without the right interpretation of such word problem may find it very difficult to answer questions on probability. But at the end of this class, I really believe that you guys will be pro and really great in solving questions around conditional probability. Before we move on to this class, quickly give this video a thumbs up. You know how important that is. And make sure you get your pen and your jotter while you get great notes out of this class. All right. As the name implies, conditional probability has to do with conditions. This implies that as opposed to all the previous questions we have been solving, where we would just say find probability of having two heads, What's the probability of having at least 2 heads? What's the probability of having or picking a queen? And all those many different questions we have solved all through these different classes. In this case, you'll be given a condition that must be fulfilled. So it makes it a bit technical because you have to fulfill that condition, and you won't get the right answer if you have not gotten or if you have not considered the condition that was attached to that question. Now, I remember I explained to you briefly in some of our in the last class the formula for conditional probability, and I told you guys that the probability of A given B, you see, as I said, A given B, a condition, is equals to probability of A intersection B over probability of B. I told you that this is what will always determine the denominator. We also have another possibility of you dealing with probability of B given A. Obviously, this will be probability of A intersection B. In this case, we don't have to be writing B intersection A or A intersection because A intersection B and B intersection A will always be the same thing. So, but in this case, the denominator will be over probability of A. All right. So this is the general formula while dealing with conditional probability. Now, I also want to remind you that if you have ever seen questions around with replacement or without replacement, it is under this subtopic. And I will be sharing with you some tips, very important tips for you to be able to always get questions around that. Now, let's see some, as we always do, let's just try and tackle some quick basic questions. All right, just some quick basic ones. And as you guys always do, I would love you to shoot back the answers. All right, so give me the answers and let's move very fast. All right, so the very first question we have here will be around just the use of this formula. So take for example, you have this question. Hello guys, am I still audible to you? Okay, all right. So given that the probability of A is equals to 0.7 and the probability of B is equals to 0.5 and the probability of A intersection B is equals to 0.35. The question is find probability of A given B. Do we have an answer? Okay, somebody says 0.7. Do we have any other response to that? Do we all agree 0.7 is the answer? Okay, let's solve together. Probability of A given B. We told you already earlier that it's equals to probability of A intersection B over probability of B. I told you already, whatever was given is what you'll be having as the denominator. So for sure now, for you to have probability of A given B, probability of A intersection B is given as 0.35. Probability of B is given as 0.5. So this would be 0.35 over 0.5, and this gives you a total of 0.7. All right, quite simple, right? Good. This is how we prefer to start. So you can start from the basics and then move on to the technical ones. Let's solve another one, shall we? We have another question that said, if probability of A given B is equals to 0.4 and the probability of B is equals to 0.5. The question is for you to find probability of A intersection B. All right, can we have the answer to this? Somebody says 0.2, another person said 0.2. All right, so let's see how we go about this. Again, we're given probability of A given B at 0.4. We know that probability of A given B is always equals to probability of A intersection B over probability of B. So obviously we know now the value of probability of A given B as 0.4. We do not know the probability of A intersection B. That's what we are actually told to find. So let's put that as, okay, let's just leave it as the same value. Probability of B was given as 0.5. So obviously you cross multiply this, you'll be having probability of A intersection B equals to 0.4 multiplied by 0.5. And this will give you a total of 0.2. All right. Again, you understand the reason why we move this way. We move from the basics to a much more challenging one. So try and always flow with the basics very well so that you will be able to understand all the concepts and get all the technicalities involved. All right, see this other question now. We have given probability of A intersection B is equal to 0.25 and probability of A is equals to 0.5. You have to find probability of B given A. Sorry, let me add this. Okay, I'll just go on to solve this. Or I could add probability of B equals to 0.3. There's a reason why I added this. What's your response here? Somebody says 0.5, somebody says 0.2, someone else says 0.5. All right. Now, the reason why I added this was to see if you guys can recollect what this formula will be. Probability of B given A will be equal to probability of course, A intersection B. In this case, over probability of A. I told you the given is what determines this. So I added this just not because it's part of the question, where I wanted to use it to confuse any viewer that is not sure. Of course, this cannot be, you will not be using this at all. So you don't actually need, this is not part of the question. I just added it there just to test your understanding. So of course, you are told to find probability of B given A. So you need to understand what the denominator will be in this case. This will obviously be 0.5 because, sorry, 0.25 because probability of A intersection B is given as 0.25 over probability of A, that's 0.5. And this will give you a total of what? 0.5. All right. So you can see exactly how we are building up this topic. So just keep on flowing. Make sure you're getting it, please, because this is key to really, we're going to solve lots of questions. So please brace up. and please flow along. Give me your solutions, please, so that we can all move together. So look at this question. We have probability of A given B is given as 0.2, and probability of B is equals to 0.6. The question is for you to find the probability of A intersection B. All right, now you should get more quicker in solving this. Get more quicker in solving this. So probability of A given B is 0.2. Probability of B is 0.6. We'll find probability of A intersection B. All right. Okay, what's the answer? 0.12. A lot of people are writing 0.12. Let's see how we go about that. So we're giving probability of A given B. Well, of course, you know probability of A given B is given as probability of A intersection B over probability of, in this case, it will be B. All right, so you have 0.2 being equals to, of course, you do not know this, and over what? Over 0.6. So therefore, we have probability of A intersection B being equals to 0.2 multiplied by 0.6, and that will give you a total of 0.12. All right, so I think this is good for introduction to the various, to this formula. I believe right now we can run now to much more, in short, other types of question. All right. Now, I need you to understand quickly that while dealing with, you will see the next level I'll be moving you guys to. Look at this question now, and then from here you'll be able to understand how to solve, because the other type we just concluded the solutions of. They are obviously probably the most simple aspect of this. And let's move on and let's see how. Now look at this. Look at this question right here. How do you interpret this question while dealing with conditional probability? So guys, I'm going to explain this. I'm sure some of you should be able to wrap your head around it already. Now you're not giving numbers, you're giving events now. So a card is drawn from a standard deck of cards. Obviously, you are asked to find a probability of getting a king given face card. Probability of getting a king given face card. Now, this is a little bit challenging if you don't know what to do. This is what I need you to understand. If you even flow through the formula I just gave you, that would obviously be king given face card will be equal to probability of king intersection face card over probability of face card. Now, I'm saying this is just me trying to be, using a layman's way, but I'm going to explain what I actually mean. This is not, you can't take this on face value, all right? But if you look at what's going on here, I want to use this to explain the whole concept. What you're going to do each time you have a question like this is that your new sample space, please pay attention, your new sample space will be this given, whatever this aspect, this in a case where you have probability of A given B. your new sample space will be this scenario. All right. And of course, this will be the intersection of both scenarios. Now, let me just tell you what this answer will be. Again, I need to remind you of how much I have said. You need to understand how events are. You need to understand the general operation of events. Like for instance, imagine I ask you to solve a question around coin, and you don't know that a coin has two faces, head or tail. Obviously, it will be very hard for you to solve any questions involving coin. Or imagine I ask you to solve a question involving dice, and you don't know that a dice has 6 different faces. Now, obviously, that's going to be a lot of issues if you don't understand the experiment itself. So in this case now, to go on, uh, to solve this question now, if you don't understand how cards work, like you don't understand what face card mean, because writing face card now, someone is probably confused there. What is face card? So guys, can anybody in the comment section tell me what I told you was going to be the event space around face cards? Can anybody give me the answer to that? Face card. Somebody said 2 to 10. Is that what I said face card was? Okay, let me get responses. Face card. I mentioned face. Thank you very much, Ademola. Marvelous. I told you that face card constitutes Jack, Queen, and King. So this is the event space when you are dealing with face cards. And obviously, the total number here, imagine this was let's take this as an event for face card. The number of elements here will be what? Can anybody give me an answer to that? What's going to be the number of elements in this event space? Somebody said 3. Somebody said 3. Can you imagine? 3? Can 3 be the answer? 3? Everybody saying 3? Wow. So the event space where you have, thank you very much, Foxy, White Mind, and the likes, Enoch and the likes. You can't have 3. Obviously, Jack has how many cards there? 4 cards. We have 4 different Jack. We have the Jack of Heart, the Jack of Club, Spade, Diamond. All right? I believe, and we have the same thing going for Queen and King. We don't just have one Queen in a stack of standard deck of cards. So obviously, the number of elements for this event when you're dealing with face cards is 12. Now, I'm sure you can understand exactly what I'm saying. And if you don't understand these operations around events, and imagine, right? So my advice would be for you to ensure you study all these events and understand them properly. Now, what I was trying to say is that when dealing with conditional probability, just like this form, King given face card, in this case, of course, you understand that you always, from all the examples you have been solving, you always have the sample space, the number of elements of the sample space as the denominator. Remember, we always say n of e over ns. All right. Now, in the case where you are dealing with conditional probability, the denominator will not be ns. That's what I want to point out here, because now you're dealing with conditions. So you are mitigating, you are reducing, you are constraining your whole experiment now to the experiment that involves just this scenario, not the whole settings, not the whole thing around the whole card. So in this case, you don't deal with the sample space as the denominator. You deal with this as the denominator. So in this case now, in this particular question, the denominator will be 12, because you can see that King given face card, the denominator will be 12. Note that. So whatever answer you're getting here will be over 12. Now, the next thing to look at, When you're looking at this question now, we have king, we have face card. King, face card. Please, guys, what's the intersection? King, face card. Can you tell me, can anybody tell me what the intersection or what this numerator will be in this case? What's going to be the numerator? So we have identified the denominator as 12 already. That will be the event space dealing with face cards. All right, you will be reducing. So let me just write this int. You reduce your sample space to condition B. That's when you are dealing with probability of A given B, obviously. So you'll be reducing your sample space to condition B. So guys, I asked the question, what's the answer? What do you feel this scenario of king and face card, what do you think happens there? King and face card. Again, someone is writing 52. I see 4/52 being written. I told you already, you cannot have the whole sample space being dealt with here. The sample, you have to reduce your sample space now to condition B. You are restricted based on this condition given. So you are not dealing with the whole scenario now. You are dealing with probability of king given face card. So in this case now, your denominator will be reduced to whatever condition B was. Now condition B said face card. So the question is, how many elements do you have that have what's the number of elements in the event space face card? We got that with 12. So I know my answer here will be equals to something over 12. So I'm trying to find whatever the numerator will be now. The numerator, again, king and face card. Now, this is the point. You know you have king. How many king do you have generally? You have 4. You have king of heart, king of diamond, king of club, king of spade. Now, this is the event space for king. Now, you have that of face card. You have jack, queen, and king. Now, look at this. What will be the intersection between these two events? Of course, all this will be present in the intersection because all this is present here, but that's all. So obviously, you are only dealing with all the kings in the intersection because you don't have jack and queen in this case. Only king was here and here. So obviously, your number of elements here in this event space will be 4. So my numerator here will be 4/12. Now, obviously, you know this is the first question on this, so and that's why it may look a bit different initially, but when we go on to solve more questions, you're going to really rock it very much more. So let's solve another question very quickly. That's the whole idea around solving. And I need to tell you that this is just a part of conditional probability. You still have other parts, like for instance, with replacement and without replacement. We'll be talking about very soon. So let's solve another question. All right. A die is rolled. Find the probability of even given number greater than 3. Look at this question now. Can anybody rock this without me solving? Let me give you like 30 seconds. A die is rolled. Find probability of even given number greater than 3. I told you already how to solve questions like this. This is your condition now. Because if you had probability of A given B, this is your B. This is the condition given B. So the condition given now is number greater than 3. So how do you solve this? Probability of even, of course, don't forget, this is the event. A die is rolled. So you don't go out of that event. A die is rolled. This is not just for every, it's not for every event that happens out there. No, this is for when you roll a die. Somebody said 1/3. Okay, Enoch said 1/3. Can I get like 1 or 2 more responses? A die is rolled. Find the probability of even given number greater than 3. Okay, Now, let me give, just because this is the starting point, I would help you with this. Somebody said 1/3 also. Let's see. When you roll a die, obviously you all know what you're going to have. 1, 2, 3, 4, 5, 6. Right? I believe nobody is here questioning this. Now, but we're not dealing with the whole scenario now. We're dealing with just this condition. Probability of even given number greater than 3. So number greater than 3 becomes the condition, becomes the, like, let me say, the new sample space in a case like this, because you are not interested in all the possible outcomes now. You are only interested in probability of even given number greater than 3. So just restrict your workings to number greater than 3. We're not interested in the whole scenario. Some people are writing 2/3. Some people are writing, I saw 1/2 there. All right, let's see how this goes. So probability of even, for you to find this, number one, what is the probability of, what is the even? Then let's probably try and find the new sample space first. What is number greater than 3? What is the event space for number greater than 3? We didn't say number greater than or equal to 3. We say greater than 3. Please note all those things. Greater than and greater than or equals to is different from just greater than. So in this case, we have number greater than 3. We have the event being 4, 5, and 6. All right, this is this. So obviously, my number of elements for number greater than 3 is what? For this event is 3. I know already that the probability of even given number greater than 3, I'm sure already that it will be over 3 because I've gotten my new sample space. All right. Now, to find what the numerator will be, do not forget, I told you guys, when you're trying to find probability of even given number greater than 3, I told you the general formula will be like probability of even intersection number greater than 3 over probability of number greater than 3. All this is the reason why we went through the basics first, why we went through solving questions around this formula. So I believe everybody in this video, I'm sure you know, everybody in this video should be, in this class, should be able to understand what we're doing right here and why this formula is happening. So this is intersection. The next thing you want to ask yourself, since we have gotten this, we've gotten the sample space, which is this event happening, number greater than 3. Let's go on to now try and find even intersection number greater than 3. So what is even? The even number we have when you roll a dice. So this is for number greater than 3. What is the even number? What is the event space we have there? Of course, you can see right here, 2 is an even number, 4 is an even number, and 6 is an even number. Look at it, oh, please pay attention. These are all the even numbers. Good. So 2, 4, 6. These are the even numbers. Now, but don't forget, please. This numerator, even intersection number greater than 3, means we are looking at these two events, these two right here. So what is the intersection of these two? Of course, the intersection is obviously, let me just say E intersection N. E means even, N means number. I'm sure you understand what I'm doing there. So what is the intersection going on here? Of course, just 4 and 6 is the intersection. So obviously, the number of elements in this intersection, the number in this intersection is what? 2. So obviously now, my probability of even given number greater than 3 will be 2 over 3. Guys, is it making sense? Guys, is it making sense? Let me come over this one more time just so that we can use this to press the point much deeper. All right? Now, look at something going on here. We have this, a die is rolled, find probability of even given number greater than 3. Guys, one of the things I told you already before is when you have a situation like this, it is always equals to even, of course, A intersection B. That's even intersection number greater than 3 over probability of number greater than 3. That's based on the formula we have always we have used already. All right. Now, guys, to find even intersection number greater than 3, the first thing you have to go and find is what is even number greater than 3? What are those two events? So for even events, we brought out, look at the dice being rolled. We brought out 2, 4, and 6. 2, 4, and 6. Of course, I believe nobody is disputing that being even numbers. Number greater than 3, we can see 4, 5, 6. 4, 5, 6. What is the intersection here? Of course, 4 and 6. 4 and 6. What's the number of elements there? Of course, you know we're always interested in number of elements in the event space. What's the number of elements there? 2. That's our numerator. Now, I told you that this 3 comes from, of course, you can see this condition, the condition that was attached, number greater than 3. Number greater than 3 now has how many elements in the event space? 3 over 3. Does it make sense? Does it make sense? Are you guys flowing? Can we go on? Okay, can we? Okay, I like that. Good. Now, because we're going to, of course, you know, we're going to upgrade the questions, and I really want you guys to know all these little ones. And guys, don't forget, we have with replacement and without replacement, one of the most popular question in almost any exam. We have it coming very soon. So 2 coins are tossed. The question is for you to find the probability. Pay attention to this now. 2 heads given at least 1 head. You can see this well. So 2 coins are tossed. Two coins are tossed. Find probability that 2 heads, of course, of having 2 heads, given at least 1 head. So look at this. Do we have answers? Two heads given at least 1 head. So I'm going to help you to better understand the formula, because I don't want to use the word probability now, since we're dealing with numbers now. So I would rather say this way for probably the person asking that question. Number 2 heads intersection at least 1 head, because it looks like somebody is getting confused with the use of the word probability here. I was just trying to use I didn't want to take you further from the expression, so I was just using that for you to be able to flow with it. But this is obviously what we have been doing. We're using the number, because when you want to find probability, I'm sure everybody understand that in the end, when you want to find probability, you use the number. So number, in this case, at least 1 head is condition, and that will be the denominator. At least 1 head. So this is what you'll be trying to solve. Looks like everybody are writing the answer 1 over 3. So first of all, that answer is correct, and I'm delighted to see that you guys have gotten very sound in this. Now, let's solve it bit by bit. You have 2 events now. I told you already that the new sample space will be at least 1 head. If you don't understand how to bring this out, or bring this out, or you know you can't solve questions like this. And that's why we had to have done the basics of probability before getting to conditional probability. Now look at it. 2 heads when you toss 2 coins. Of course, the sample space generally when you toss 2 coins, I'm sure you guys remember it. HT, TH, and TT. Anybody disputing this? I'm sure no one. Now, at least 1 head. At least one head. What's the event space of at least one head? At least one head, the event space. Bring out the event space here. The event space of at least one head, we have two head being involved. We have HT being involved. We have TH being involved. The only thing that will not be included is TT because they said at least one head. Two head is permitted, one head is permitted, but zero head is not permitted. All right, this is the event space for that. Now, two heads. What's the event space for two heads? The event space for two heads is obviously going to be just HH. We don't have two of that. Or do we? No, we only have one HH. So now look at what we're doing right here. This is the event space, the total sample space when two coins are tossed. We are now given a condition. We are asked to find the probability of two heads, given that at least one head, with a condition of at least one head. Now, I told you already that this at least one head becomes your new sample space. That will be the denominator of your answer. So, to get this answer, numerator over denominator, what numerator is for you to get this. Two heads intersection, at least one head. This is two head, HH. This is at least one head. HH, HT, and TH. Guys, what's the intersection between this and this? The intersection is obviously HH because that's the only two things common here. So the intersection of this is HH. Just these things I start with. That's only what is common in both of them. You know the meaning of intersection already. What you can see in this event and you can see in this event. And so the intersection, let me just write it as N. Intersection, understand what I'm writing here? This is the intersection, HH. Now, how many elements do you have there? Don't forget, how many elements do you have there? Just one. The number of elements there is just one. So this answer will obviously be 1 over. Now, how many elements do you have in your event space for at least one head? This is at least one head here. 1, 2, 3. You have 3. So the answer is 1 over 3. Is it making sense, guys? So guys, how do you feel about this? Is it making sense? All right, so we're going to use more questions to get your understanding much deeper. Look at this question again. In a class of 50 students, so we have 50 students in a class, we're told that 30 study maths, 20 study physics, and 10 study both. The question is for you to find the probability of maths given physics. All right, so let me see who is going to solve this quickly. And while you are doing that, if you are here to give us a thumbs up, please do that as soon as possible. Let's get this thumbs up to a very high number. Guys, give me the answer to this. In a class of 50 students, 30 study maths, 20 study physics, 10 study both. Find probability of maths given physics. All right, now look at what we have right here. Very simple. This is probably the simplest here that we have solved in the past 2 or 3 questions. Probability of maths given physics will obviously be probability of maths intersection physics over probability of physics. All right, you can understand what we're doing right there. Now, what's probability of maths intersection physics? What's the number of you understand what I'm trying to say there? What's the number of elements in the event space? The event space for maths we said 30 of them, there are 30 students in that event space. The event space of physics, we said there are 20 events. We're told that the event space for both of them, we had 10 people there. So the event space for both of them, that means the intersection. This use of the word both here indicates their intersection. That means it includes this 10 now has both math and physics included. So that's what will serve for your M intersection P. So we have 10 here. All right. Now, the denominator, probability of physics. Now, probability of physics is obviously this in this case. So that will be 10 over 20. The total answer will be 1 over 2. All right. So take this very quickly also. Let's talk very fast. From a group of 100 people, now we are moving into a bit faster while solving. So please just shoot your answers to me. From a group of 100 people, "60 like football, 40 like basketball, 25 like both." The question is probability. Find the probability of football given basketball. Do we have that in like 3 seconds? Find the probability of football given basketball. Somebody wrote 5 over 8. Do we have other answers? From a group of 100 people, 60 like football, 40 like basketball, 25 like both. Somebody wrote 5 over 12. Somebody wrote 5 over 8. Let's see this very quickly. Of course, the total sample space is 100. But in this case, that will be very irrelevant for this particular question because you do not need this sample space. I told you already when you have a question like this, the new sample space will be that of basketball. So obviously this will be probability of football given basketball will be equal to probability of football intersection basketball or probability of basketball. Intersection between football and basketball is giving us that has the both. 25 like both. That means football, basketball, both. So we have 25 over probability of basketball, we have 40. This will give you a total of 5 over 8. All right. A bag contains 5 red and 7 blue balls. And 7 blue ball. All right. One ball is drawn. One ball is drawn. Now the question is find the probability of red given ball is not blue. Let me see who is going to tackle this question effectively. A bag contains 5 red and 7 blue balls. A bag contains 5 red and 7 blue balls. One ball is drawn of course, from the back. Find the probability of red given that ball is not blue. Okay, can you guys tell me, those of you, I can see majority of you are writing the answer as 1. Can you tell me how you got 1? What was your numerator? What was your denominator? How did you arrive at the answer 1? Probability of red given that that ball is not blue. Can you tell me? Okay. All right. Now look at this. This is a question that you have to, of course, you understand. I believe somebody made a comment in probably the first class that probability has a lot to do with English. That's absolutely very true. You being able to interpret questions is almost as important as knowing how to solve questions. Look at the question. Find probability of red. Of course, if you wanted to, ball is not blue. That's a major element in this room. Ball is not blue. What does it mean? What does this statement mean, guys? What does this statement mean? What can you interpret this statement as? Ball is not blue. Ball is not blue. So you are having a bag that contains 5 red and 7 blue. So when the question say ball is not blue, thank you very much, Akonde Praise. That means ball is red. It's just a twisted way of saying ball is red. So ball is not blue means ball is red. So now, that being settled now, it's like having probability of red given, let me just write it as NB, not blue, is also equals to probability of red given red. So if you say probability of red given red, that will obviously be probability of red intersection red over probability of red. If you're following the formula approach, red given red intersection red will be what? Red. You have red events. Let me assume, of course, you have 5 red balls. Let me say red 1, red 2, red 3, red 4, red 5. You have another, you are now saying you are doing the intersection of red with red. Of course, you'll be getting red also. You're getting everything in here. And how many events, what's the number of elements in that event space? Of course, 5. Probability of red, of course, number of elements of red is also 5. That'll be 5 over 5. That will give you 1. It's that simple. Okay, so I believe we have made so much progress. Can I get feedback from you guys? How do you feel? Are you getting the point? Because very soon we're moving into with replacement and without replacement. Okay, all right. Okay, okay. All right, I love those feedbacks. All right, take this very quickly. A card is drawn from a standard deck of 52 playing cards. Find the probability that the card is queen, given that it is a red card. A card is drawn from a standard deck of 52 playing cards. So a card is drawn from a standard deck of 52 playing cards. find the probability that the card is a queen. The card is a queen, given that it is a red card. This is obviously conditional probability. So I'm seeing different answers. 1/2, 1/13, 1/26, 1/13. All right, we'll see which is correct. So I wouldn't bother writing the question. I believe you all heard me correctly. A card is drawn from a standard deck of 52 playing cards. Find probability that the card, look at now, probability that the card is a queen, given it is a red card, is what you are told to find. Of course, you know this will obviously be probability of queen intersection red over red. This is based on the formula, which I believe a card is drawn from a standard deck. For that person that wants me to read the question again, a card is drawn from a standard deck of 52 playing cards. Find the probability that the card is a queen, given that it is a red card. Now, if you look at this question, this is the question. Find the probability of it's a queen, given it's a red card. Of course, this is the use of the formula. Probability of queen intersection red over probability of red. Now, if you do not understand, of course, the event of cards, queen, red, and all the likes, of course, this is going to be a very tough one for you. Now, what's the event space? What's the total element of the event space for queen? The total element there is what? We have how many queens? We have 4 queens. 1 for, let me write it this way. We have queen for heart, we have queen for diamond, we have queen for spade, we have queen for club, right? This is the total queen. This is total number of queens we have. Now, what's the event space for red cards? I told you guys that for red cards, we have 2 different cards, 2 different suits, 2 suits that are red. Number 1 is diamond. Number 2 is hearts. So we know these are the 2 different cards. And don't forget, each of them have a total of 13 cards. So that means the number of elements here will be 26 that are red cards. All right? I'm sure you guys are flowing with this. Now, without wasting time, number of elements in the event space of red cards is 26. I know already that my denominator is 26. I told you guys already that when you are dealing with conditional probability, your sample space goes from all the 52 that you know was a general sample space. Your sample space will evolve to that of the condition. It will be showing forth the condition that was attached to this your probability, which was red. That will be your new sample space. That's how we got 26, because number of elements in the event of red cards is 26. Now, to understand the numerator, which will be the probability of the queen intersection red, the question to ask yourself is, this is the red cards. We have diamond, we have heart. How many of them are queen? Of course, what's the intersection between the queen card and the total number of elements, all the elements in the queen event space and all the elements in the red card event space? If you look thoroughly at this, you will see that for diamond you have 1 queen. Don't forget, for heart you have 1 queen. So this, we have diamond's own queen here, we have heart's own queen here. So the intersection will be just these 2, that for heart and that for diamond, which is present in this event space and also present here. So the total number of elements that are present here and present here is obviously 2. So the intersection is obviously 2 elements. That will be, the total answer will be 2 over 26. So 2 over 26 will be your total answer, and that will be 1 over 13. That's how it works. All right. A fair die is rolled. A fair die is rolled. A fair dice is rolled. So a fair dice is rolled. A fair dice is rolled. You have to find the probability that the number is a multiple of 3, given that it is even. So a fair dice is rolled. If a fair dice is rolled, find the probability that the number is a multiple of 3, given that it is even. So we are still following the same pattern of what we have been solving. A fair dice is rolled. So we have different answers coming in. We have 1, we have 1 over 3, we have 1 over 6, we have 1 over 3, we have 1 over 6. All right, let's examine this quickly. A fair dice is rolled. Find probability that the number is a multiple of 3. Probability that multiple of 3, given that it is even. So you can see the condition they attached. So without even wasting time, I already know that you know how this works. Let me just write it as PM and E. So PM given E is M intersection E over probability of E. Now, a fair dice is rolled. What's your sample space there? 1, 2, 3, 4, 5, 6. All right. Now, probability that it's a multiple of 3. The question is, what is the event space for multiple of 3? Let me write E3, showing the multiple of 3. Multiple of 3 we have here, we have 3, we have 6. All right. Now, given that even the event space for even, let me write EE, showing even. For even, we have 2 is an even number, 4, and we have 6. So, of course, now the intersection of multiple of 3 and even will be what? We have 6 alone as the intersection of course, the event that has to do with multiple of 3 and also even. We have only 6 being present. Now, go on now to solve this. I told you already, probably the one that has to do with the even will be the denominator. I told you the condition determines the new sample space. So my answer is over. New sample space is what? Even. That's 3. What's going to be what's my intersection? How many elements do we have here? 1. That's 1 over 3. Are you seeing how this thing works? It's about understanding the process and never mixing things up. It's that simple, guys. And that's the reason why I'm trying to expose you to lots of questions so that you can get much more better. With each question, you have the opportunity to improve. All right. Look at this question. 2 fair dice, 2 fair coin are tossed. 2 fair coin are tossed. So the question is for you to find the probability of getting exactly 1 head, given that at least 1 head occurs. Look at this question. Let me see how you will solve this. 2 fair coin are tossed. 2 fair coin are tossed. Find the probability of getting exactly 1 head, given that at least 1 head occurs. Somebody said 2 over 3. Somebody else said 2 over 3. Are you sure that's the correct answer? Now let's follow the same process. Two fair coins are tossed. So of course we have the sample space. These are things that, of course, at this point, I believe everybody in this class should be in proper understanding of what's going on. This is a sample space when two fair coins are tossed. So you have to find the probability of getting exactly one head, given that exactly one head. So event space for one head, let me write 1H. Exactly one head. We have just two events, two outcomes that produces exactly one head. Look at the word, though. They didn't say at least one head, exactly one head. HH cannot be part of that event. HT can be part of it because this is exactly one head. TH is also part because that's exactly one head. TT can never be part. So we have this as the event space, all right? So the question there is, what's the number of elements for this event? For this particular event, we have 2. Good. Now, given that at least one head occur, that's another scenario now. So how do we write this? A1. Let me just write A1. Just you understand what I'm doing there. I'm just trying to name it accordingly. So at least one head. At least one head. What's the event space for at least one head? Of course, we are okay with HH because that's part of at least one head. HT, TH, and that's all. TT is the only exemption because we don't have at least one head there. What's the number of elements for this particular event? We have 3. Good. Looking at this question, probability of getting exactly one head. One head given at least one head. Of course, this will be probability of one head intersection at least one head over probability of at least one head. This obviously will be, what's probability of at least one head? At least one head, we have 3. That will be over 3. The sample space will be over 3. Now, the intersection between at least one head and one head exactly. One head, exactly one head. Look at it here. Exactly one head. This is it. At least one head. This is it. What's the intersection? E1H intersection EA1. These two events, if you're intersecting this, what's going to happen? Of course, we have HT and TH. This and this. This is common here. This is common. These are the two things that are common to both of them. What's the number of elements we have there? Just not to waste time, you know that that's 2. So this obviously will be 2 over 3. Hope it's making sense. Hope I'm not confusing anymore. Hope you are able, hope you are following, right? Hope it's making sense. Hope it's making sense. This is how you tackle questions. A number is selected at random. A number is selected at random. So a number is selected at random. From 1 to 20. So, okay. So you have to find a probability that it is a prime number given that it is odd. So a number is selected at random from 1 to 20. Now to find the probability that it is a prime number given that it is odd. A number is selected at random from 1 to 20. Find the probability that it is a prime number given that it is odd. A number is selected at random from 1 to 20. Find the probability that it is a prime number given that it is odd. What are the answers you have there? Okay. So what are the answers? Somebody wrote 7 over 10. Somebody wrote 7 over 8. Somebody wrote 7 over 10. All right. Let's see how we solve this. A number is selected at random from 1 to 20. Find probability that it's a prime number between 1 to 20. What's that event space? Prime number. Event space of prime numbers. 2, 3, and we go on to have 5, 7, 11, 13, 17, 19. These are all the prime numbers between 1 to 20. What's the number of elements in that event space? 1, 2, 3, 4, 5, 6, 7, 8. We have 8. Now, this is for just the prime numbers. Now, it is odd, this other one, given that it is odd, the event space for odd numbers between 1 to 20. Of course, 1 is an odd number, 3 is an odd number, 5, 7, 9, 11, 13, 15, 17, 19. These are all the odd numbers. All right, between 1 to 20, don't forget. Now, you're told to find the probability that, look at what you're trying to find, probability that it is a prime number, given that it is odd. Because this will be probability of prime number intersection odd number over probability of odd number. So, what's the number of elements for odd numbers, by the way? Number of elements here, what do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 elements. I know automatically that my denominator will be over 10 because I told you already that whatever the condition was is what your new sample space will carry. So what is prime number intersection odd number? Look at these two events. What is their intersection? Of course, we have 3, 5, 7, 11, 13, 17, 19. How many elements do we have there? 1, 2, 3, 4, 5, 6, 7. So your answer will be 7 over 10. All right. Can you see how nice and simple this is? So at this point now, I'm not expecting that there's anybody struggling with this aspect. So very soon we'll be leaving this concept now. Let's just solve some more so that at least we can get very solidified in this. I believe everybody now should be able to follow what's going on. Conditional probability is what we are still on. So a letter is chosen at random from the word probability. So a letter is chosen at random from the word probability. A letter is chosen at random from the word probability. Find the probability now that the letter is a vowel. Find probability that the letter is a vowel, given that it is not a consonant. So, it said letter is chosen at random from the word probability. Find the probability that the letter is a vowel, given that it is not a consonant. Okay. Adebola said 1. The letter is chosen at random from the word probability. Find the probability that the letter is a vowel, given that it is not a consonant. Every other person is saying 1. Now, of course, you know this will be probability of vowel intersection, not consonant. I'm sure you understand what's going on. Not consonant over probability of not consonant. Now, I asked you in a question we solved some minutes back. I said, when you say not consonant, what is not consonant? If they said not consonant in the alphabet, if something is not consonant, what's it going to be? Of course, it's vowel. You know that we only have 2 sections for your alphabet. We have consonant and vowel. So obviously, when they say non-consonant, it's more like saying vowel intersection vowel. This still vowel. This still vowel. And so when you see questions like this where you're having to like, just know your answer will be 1 already. But for those of you that need to see what's going on here, How many vowels do you have? A, E, I, O, U. Right? But looking at from your word probability, we have 1, 2, 3, 4. All right. So we have 4 different scenario there. 4 of them, if you are intersecting with the same 4, it will still be 4. And then over 4, it will be 4 over 4. Just that simple. I'm sure you understand what's going on. All right. A number is chosen is selected at random from 1 to 30. A number is selected at random from 1 to 30. A number is selected at random from 1 to 30. Find the probability that it is divisible by 5, given that it is divisible by 10. Find the probability that it is divisible by 5, given that it is divisible by 10. So everyone is writing 1, 1, 1, 1. Okay. It looks like this class is really, I really love the vibe. I love you guys really are understanding. That's really good to see. So the number is divisible by 5. That's the first one, divisibility by 5. Between 1 to 30, you actually say what numbers are divisible by 5 there? Because you have 5, 10, 15, 20, 25, 30. Now, given that it is divisible by 10, divisibility by 10, we have 10, 20, 30. These are the 3 numbers that are divisible by 10. So, of course, you know that probability that it is divisible by 5, given it is divisible by 10, will be equals to probability of 5 intersection 10. You understand what I'm doing there? I'm just using these nomenclatures can vary from whoever is solving it. So you don't have to say you have to write the same thing I'm writing, as long as you are flowing with the right thing. So in this case now, if you look at what we have here, the intersection between 5 and 10, we have 10, 20, and 30. All right. How many elements do we have there? We have 3. Probability of 10, the 1 of 10. How many elements do we have for just 10? We have 3. This is 3 over 3. That's 1. It's that simple. A card is drawn from a standard deck. Find the probability it is an ace, given that it is a black card. Find the probability that it is an ace, given that it is a black card. Find the probability that it is an ace, given that it is a black card. So a card is selected from a standard deck. You have to find the probability that it is an ace, given that it is a black card. Oh, this aligns more with our standard A given B. So find probability that it is an ace, given that it is a black card. Somebody wrote, Precious wrote 1 over 13. Okay, do we have other answers? A card is drawn from a standard deck. Find the probability that it is an ace, given that it is a black card. Do we have other answers? Of course, this would be probability of A intersection B over probability of B. So you go on to find your black cards. Of course, that's your sample space in this case. What is the event space for that? Black cats. Don't guys, can you remind me what did I tell you about black cats? How many elements do how many cards do we have that are black cards when dealing with a standard deck of cards? Black cards. How many do we have? Of course, we have 26 because we have that for spade and that for club. And for spade, we have 13 cards. For clubs, we have 13 cards. So the total element of in the event space for black cards is 26. So I know that this answer will be over 26 already. All right. Now, how many cards are what's the of course what's the ace? Well, how many aces do we have? We have 4 different aces, don't forget. We have ace for diamond, we have ace for heart, we have ace for spade, we have ace for club. Don't forget. Now, among these aces that you have, what's going to be the intersection between the ace and the black card? Of course, what are the elements present here that are present here? For your spade, you have your spade and you have your club. This is the only two that will be both here and there. So we have 2 elements there. So this will be 2 over 26. That will be 1 over 13. Guys, how do you feel about this? Is it solvable? Do you feel you can tackle anything at this point? Conditional probability, how do you feel? So I think we have solved something similar, but just to refresh your memory, A intersection B is 0.2, probability of B is 0.4, probability of A given B. Just 1 second, give me your answer and let's move on. All right, 0.5. So obviously that will be 0.2 over 0.4, 0.5. All right, guys, now we're going to move to with replacement and without replacement. Now, this is the place where I'm going to tell you to pay real attention because this is probably the places where you tend to get the most number of questions from. All right, so when dealing with replacement and without replacement, I want you to understand that once you see those statements being mentioned, they are very key to getting your solution. You need to be very, very careful of reading properly if it said with or without replacement. Now, with replacement, it's more like say we have 10 balls in a basket. 10 balls in a basket. You have a basket, there are 10 balls there. If you dip your hand inside this basket and pick one ball out, now the solution while dealing with probability will vary depending on if they said you replaced it back or you did not replace it back. So if they said you replaced it back, it's more like say you had 10 balls here. Let's say these are 10 balls inside here. If you pick the ball out of this place, of course, there are 9 left, minus 1. Now, if you did not replace it back, the new sample space will no longer be 10, will now be 9. Now, if you replace it back, the sample space will remain unchanged. Now, I want you to understand that I believe you understand already the importance of sample space and how that affects all your work. If you cannot be able to successfully bring out the sample space from any question, it is just sure you cannot get that right. So now, if you fix back your ball, of course, you get your sample space normal. It's constant, it doesn't change. But if you did not put it back, you must use the new sample space as 9 in this case. Now, I need to say one thing. One of the technicalities that used to come out is that they can tell you now, for instance, that these 10 balls, we had 3 black, we had 7 blue, for instance. Now, I need you to also understand that if the ball you picked was a blue, so let's say you wanted to find probability of getting a blue from this first pick. Let's say you had 10 balls, 3 black, 7 blue. Please make sure you are paying attention. You have 10 balls, 3 of them were black, 7 of them were blue. They asked you what's the probability of picking a blue ball initially. Of course, that will be, you have 7 blue ball, 7 over 10. Number of course, the blue ball, the event there is blue ball. So the number of elements in that event space is 7. Number of elements in the sample space is 10. The total number of possible outcomes, right? 10. So this was your probability when you were dealing with the first pick. But let's say, for instance, now they tell you that you did not replace the ball back. They said you picked the ball without replacement. You drew a ball from this basket without replacement. Obviously, you understand that. Now, look at one thing that will happen. The sample space will change from being 10 to 9. And also, don't forget, this 9 is going to be with a new different division. It will now be 3 black and 6 blue, because you already picked a blue. So these are the tricks you need to know very well when dealing with replacement or without replacement. You need to understand that you don't just pick ball and just ignore what happens. You need to pay attention to, okay, what was the color of ball I picked? If you picked blue in the first pick, you know that your sample space of blue, or probably let me say rather, your event space of blue has reduced from, in this case, 7 to 6. So your second drawing of a ball from this basket will not be over 10, number one. And also, if you were told, let's say for instance, you are told to find probability of picking a blue and a blue as the second, that means blue, blue. Now, blue, blue will be 7 over 10 as the first blue, because in that case, you are not picking anything. 7 over 10, 7 blue over 10, total number of possible outcomes of 10 balls. And now, for this second blue now, if you were having without replacement, your total number of possible outcomes, your sample space is no longer 10, it's now 9. And also, your event space will no longer be 7, it will now be 6. That's the way you deal with replacement and without replacement. Now, let me say another thing. Let's say they said you pick the blue as a first drawing, you pick the blue as a second drawing, and you now picked a black, and you now picked a black as the third drawing. Now, look at what happens in this case. You pick the blue as the first. This highlighted the probability. You picked a blue as the second. This highlighted it. Your sample space has reduced. Your event space for blue has reduced. Now, you are picking a black as the third drawing. Now, look at what's going to happen. And when you say and the probability, you use a times. When you say or, you use a plus. Now, and you are picking blue and black. Now, this black now, your sample space will no longer be 9, because don't forget, you drew one ball first. You were left with 9. You are drawing 9. You're drawing from 9, the second draw time you are drawing. So the total number of possible outcomes for the second drawing was 9. Now, if you are going to pick again the third time, you will not be having 9 there again. Of course, you have picked 1. Don't forget, we're dealing with without replacement. So you'll be having the sample space of 8. Now, but you are dealing with a different event now, not the same blue. So your blue is going to be left with 5 because you drew 1, you reduced it to 6, you drew another 1, you reduced it to 5. So at this point now, at this present picking, this third pick, you had 5 blue ball, you had 3 black ball. Of course, make it a total of 8. All right. Now, but don't forget, you are drawing a black here. So your event space for black is still intact, 3, because you have not drawn any black at all. All right. You have not drawn any black at all. So your event space remains as 3. Now, I'm going to give a question now, guys. Imagine I'm going to draw the 4th time. What's the probability of drawing a blue the 4th time? Of course, add what's going to be the mathematical expression for drawing a blue. Somebody said 2/7, somebody said 5. Many people are saying 5/7. Now, if you look at this, after drawing this black, this third time, you're left with 2 black and you still had your 5 blue. This next picking now, drawing, you only have a total of 7 left. Only 7 balls are left now. And in your blue, you only have 5 blue left. That will be 5/7. This is how you understand this thing. Now, I'm going to ask again, what's going to be the outcome for drawing a black as the next draw? A black. Okay, now black, of course, you are left with, you don't forget you have drawn a blue here, so you are left with 4 blue and 2 black. So your black now will be 2/6. Guys, this is the whole concept around without replacement. You must go on in subtracting what you have picked from your sample space and also from your event space. If you pick the red, go to the event space for red and remove it. This is a pitfall for many students because students sometimes, while they are in an exam or probably due to pressure or, these are questions that you see a very simple question and you come out from the exam hall and you're wondering why you did not get the answer. Probably you did not subtract from the event space. Probably you did not subtract from the sample space. All right. That's a very key introduction to without replacement. Let's try and solve some questions now. All right. Now, you need to be very smart while solving all this. Anything around conditional probability, you have to be very, very smart. You cannot just solve logically. You have to solve with you. Like what I mean logically, I mean you cannot just solve on face value. All right. Look at this question. Let me see how you fare with it. A bag contains 5 red and 7 blue ball. Now, in this case, they said 2 balls are drawn without replacement. Key. The key here is the word without replacement. If they told you with replacement, it's a total different ball game than without replacement. So the question now for you is to find the probability that the second is red, given that the first is red. This is the question. Can anybody give me a solution quickly? A bag contains 5 red and 7 blue balls. 2 balls are drawn without replacement. Find probability that the second is red, given that the first was red. You have to be very smart to answer these questions. You have to understand the whole general concept around conditional probability. So look at the question. You were told that we have a bag containing, somebody said 4/11. Can we get all the answers? A bag contains 5 red and 7 blue balls. 2 balls are drawn without replacement. 2 balls are drawn without replacement. Somebody wrote 5/33. Okay. 2 balls are drawn without replacement. Now, what's the probability of having the second being red, given that the first was red? Guys, this is quite very important. 5/33. The other person to say 5/33. Now, you don't have to solve this. You don't have to be hard on yourself. Look at this. Given that the first was red. After you removed, because they said the first was red now. So your sample space here, generally, without you having this any drawing, without you drawing any ball, you had 5 red and you had 7 blue, making your sample space to be 5 plus 7. You had 12 different balls. Your sample space was 12. But when you drew the first ball, your first ball was red, right? Your sample space reduced to 11. So you had -1. So this, given that it was red, the sample space associated with this condition is 11. So your answer will be over 11. Now, don't forget, you have already drawn also a red ball. So that will be 4/11. That will be 4/11. That's the way you solve these questions. You have to be very, very intelligent. Read through all the question. A bag contains 5 red and 7 blue. 2 balls are drawn without replacement. Key, without replacement. Find probability that the second was red. The second was red, given that the first was red. The second was red, given that the first was red. So in this case, what you're doing right here is to, number one, understand that given that the first was red, in this case, your sample space after you have picked the first as red is 11. And you are left with the event space for second being red. You are left with only 4 left. That's 4/11. Okay, of course, this is the first aspect under this. So you can obviously wait for more questions and then you get better at it. So look at this next question. A bag contains 4 white and 6 black balls. A bag contains 4 white and 6 black balls. So the question is for you to find the probability that the second is white, given that the first is black. So a bag contains 4 white balls and 6 black balls. So you have to find the probability that the second is white, given that the first was black. We have 4/10 being written. Somebody else wrote, I think, 1/10. Somebody wrote 4/9. Somebody wrote 4/9. Somebody wrote 3/10. All right. Let's solve together. Now, a bag contains 4 whites and 6 black balls. In this case, the sample space is obviously going to be having a total of 10 balls. The question said find a probability that the second ball was white, given that the first was black. So you have picked a ball from this bag, and they told you that the ball you picked was black. So obviously, one ball is taken out. You are left, your sample space is left with 9. The answer will be over 9. I'm sure of that already. Now, second being white. Of course, you have not picked any white. You have only picked black. So from your white balls, you still have your white balls. You still have your total white ball. It's only your black that has reduced. You had 6 black. Your black has reduced from 1 to 5. Or you still have your white intact. You have not picked any white. So obviously, the answer will be 4/9. You see exactly how this works. So this is exactly how it works, all right? You have to follow the process and you can never go wrong, all right? So let's see another question. You know how I always love to do it. Ensure you solve as many as possible so that you are very sound in every different scenarios possible. So 2 cards are drawn without replacement. 2 cards are drawn without replacement. 2 cards are drawn without replacement. We have to find the probability of so 2 cards are drawn without replacement. So you have to find the probability of having the second king, given that the first was a king. Given that the first was a king. All right, so 2 cards are drawn without replacement. Look at the keyword here, without replacement. So the whole point, as I told you already, is looking at this word. Is it with replacement? Is it without replacement? So 2 cards are drawn without replacement. But to find the probability that the second was a king, given that the first was a king. So how do you solve this? Probability that the first, you got the first as a king. What's probability that the second was a king, given that the first was a king? Now looking at this, of course, very simple. Number 1, 2 cards are drawn without replacement. Now, of course, you know, in this case, you are dealing with 52 different cards. I told you guys already, once you have an issue with understanding the experiment being carried out, it's very difficult, if not impossible, for you to get the answer. So when you're drawing 2 cards, of course, you know the sample space for a standard deck of cards to be 52. All right. Don't forget, 52 is the general sample space when you are trying to draw cards. Now, the first was a king, of course. What is the event space for kings generally? We have just 4 kings, don't we? We have 4 kings generally. Normally, we have 4 kings. What's the probability of you getting the second one as a king, given that the first was a king? Now, the first was a king. That means out of these 4 kings that were existing before, you are having a deficiency of 1 because the first was already a king. And of course, if you have the deficiency of 1 king, of course, your cards reduces from 52 to 51. This becomes 3. So the probability of second being king, given that the first was king, will obviously be equals to 3 over 51, which will be 1 over 17. You can see how this goes. It's all about the concept. It's all about the concept. I need to submit to you that there is still a different one, of course, similar to the kind I used to explain initially. But I want us to exhaust this so that you guys can be very sound with this. So look at this question quickly. A bag contains 3 defective and 9 good items. A bag contains 3 defective So a bag contains 3 defective and 9 good items. So we have 3 defective and we have 9 good items. I'm sure you know what good defective items are. Those are the items that are not perfect and not with the standard grades. So the question is for you to find a probability that the second was defective, given that the first was good. The first was good. So a bag contains 3 defective and 9 good items. All right. So in this bag now, what's going to be our total sample space? Our total sample space will be, of course, 3 defective and 9 good items. That's 12. All right. So we have 12 total goods items. Now, among those 12 items, we have defective 3, we have 9 good. So the question says you should find the probability that the second was defective, given that the first was good. Now, if the first was good, you of course you're trying to look at it. The first was good already, so you're obviously dealing with 11 items now because you already picked the first as a good one. So you are left with 11 items. Of course, the good ones we had 9 initially. The defective one we had 3. You've succeeded you've taken 1 out of the good one, so we are left with 8. But the defective is still intact. It's still 3 defective left. So this probability of the second being defective, given that the first was good, of course, the sample space for this second pick you are trying to have will be 11, not 12 anymore, because you have already picked the first as good. And then the second defective, the numerator, of course, the event space for that will be 3. So this gives you 3 over 11. So this is how it works. You just have to be very solid. From 6 red and 4 green ball, from 6 red so from 6 red and 4 So from 6 red and 4 green ball, 2 are drawn. from 6 red and 4 green ball, 2 are drawn. So we have 6 red and we have 4 green. So 2 are drawn. So the question said, what's probability that the second is green given that the first was green? So the question said you have 6 red, 4 green, 2 are drawn. What's probability that the second is green given that the first was green? All right, look at what we have here. We had a total, the sample space here was 10 because of course you understand the both colors is a total of 10 different balls. Now, when you're dealing with this, the first was green already. So this your green ball from 4 will be reducing to 3. And of course, if it's reducing to 3, we have 6 plus 3. Your new sample space will be 9. So the probability that the second will be green will be something over 9. Second being green, you don't have your 4 green anymore, you have only 3. That'll be 3 over 9. That'll be 1 over 3. So I told you guys already that we have different category of questions we can have under these topics. So this is just one of it. This is not everything. You can really have other types where you are even asked to pick 3 different scenarios. This is just when you are having, you can see that we have been consistently picking just 2. That's just because I'm trying to ensure you are perfected in that first. You have other scenarios where you are picking 3, all right? When you're picking 3. And don't forget, in this case, you are actually dealing with a condition. So you will be seeing other examples very much more. A bag has 3 white and 5 black balls. So 3 white, 3 white, and 5 black balls. Three white and 5 black balls. The question is for you to find the probability that the second was black, given that the first was white. All right. So how do you find that? Somebody said 4 over 8. Somebody said 5 over 7. Somebody said 5 over 7. So a bag has 3 white and 5 black balls. What's the probability of the second being black, given that the first was white? 4 over 8, 5 over 7, 4 over 7. Okay, look at this. What's your total sample space? What's the sample space rather? Total number of possible outcomes here, we have 8. All right. Now, you already picked the first as white. So obviously, your white balls, your event space for white will reduce to 2. And of course, you now have your sample space reducing also by 1 because you have already picked 1 white. So you have 7. So the probability of picking the second as black. Second now as black, your event space for black is 5. That will be 5 over 7. So that's the way you tackle questions without ever missing it. 2 cards are drawn. 2 cards are drawn. 2 cards are drawn. Find the probability that the second was ace, given that the first was not ace. Find the probability that the second was ace, given that the first was not ace. Let me see how you fare with this. Let me see who gets this. Two cards are drawn. Two cards are drawn. Find the probability that the second was ace, given that the first was not ace. Two cards are drawn. Find the probability that the first, of course, the second was ace, given that the second, find the probability that the second was ace, given that the first was not ace. Now, I told you already, if you do not understand how cards are, you can't solve this question. So the total sample space for cards is 52, all right? First was not ace. So let's say we had ace and we had what is the general number of elements that are ace? We have 4 aces. Of course, I told you already, heart, diamond, spade, club. Now, the first was not ace. That means you did not use the ace at all in that case. You did not pick from the ace. You picked from other ones, not ace. That means you probably, of course, those that are not aces will be 52 minus 4. Not ace will be 52 minus 4. But again, that's not very relevant because you were not asked question around not ace. So you picked something from here, 48 different cards. So you had 48 cards here. The first pick was from this 48. So you're left with 47 here. But of course, your sample space also reduced by 1. So you're left with 51. So the question is, what's the probability that the second one you pick was going to be ace? Of course, your sample space will now be 51 because you already picked one already, but it was not ace. So your ace still remains as 4 for the event space. That will obviously be 4 over 51. Let's please give about 5 minutes just to consolidate what we're doing right here. Just 5 minutes. Probably we can do a more of speed responses now without so much of, now that I believe many people are flowing with what we're doing. From 5 blue and 5 yellow ball, 2 are drawn. Find probability that the second is yellow, given that the first was blue. Can you flow that way? I just read the question without writing. So from 5 blue and 5 yellow ball, 2 are drawn. Find the probability that the second was yellow. Probability that the second was yellow, given that the first was blue. All right. So don't forget, they said from 5 blue and 5 yellow ball, 2 are drawn. 5 blue and 5 yellow ball, 2 are drawn. So we have a total, the sample space there is obviously 10 initially. And we have blue being 5 and yellow being 5. So blue is 5, yellow is 5. So the probability that the second pick was yellow when the first was blue. You have already picked 1 blue, so you're left with 4 blue. The sample space also we have to reduce by 1. So the second being yellow will be 5 over 9. And you see how very interesting this is. It's all about being focused. So a box contains 2 red, 3 blue, and 5 green balls. Now you have 3 different ball color. A box contains 2 red, 3 blue, and 5 green balls. Find the probability that the second is green, given that the first was red. Find the probability that the second is green, given that the first was red. A box contained 2 red, 3 blue, and 5 green. Red was 2, 2 red, 3 blue, and 5 green. Alright, so the question says you find the probability that the second was green, given that the first was red. Second green, first given that first red. Of course, looking at this now, you can see that the second being green, given that the first was red. If you picked red, right, of course, your total sample space here is what? 10. You're picking one already, red. You picked one red, you're left with only one red. You're left with 9. Your sample space is now 9. So given that second being green will be 5 over 9. You can see how nice and simple this is. So from 10 balls, speed now, you guys just shoot me your answer. We need to consolidate this, guys, so that we are not going back into this aspect. I don't expect us to do so much on this anymore, except if we're just asking random questions, but not for teaching. All right. From 10 balls, don't worry, we're leaving very soon. From 10 balls, 6 whites, 4 blacks. 2 are drawn. Find the probability that the second was white, given that the first was white. The second is white, rather, given that the first was white. You have to find the probability that the second was white, given that the first was white. You had 10 balls. White was 6. Black was 4. What's the probability that the second is white, given that the first was white? Your sample space, since you have picked the first white, you are left with just 5 whites. And you are left with only 9. So your answer is still the same what? 5 over 9. Two cards are drawn. Two cards are drawn. Find the probability that the second is queen, given that the first was jack. Two cards are drawn. Find the probability that the second was queen, given that the first was jack. Two cards are drawn. Find the probability. At this point, I expect the correct answer to be related back. I'm expecting that everybody now has understood what to do. So this is just for consolidating what you know already. I love I'm seeing uniform answers. Two cards are drawn. Probability that you have to find probability that the second was queen, even that the first was jack. Of course, 52 cards in all. When you pick the first as jack, you are left with 51. The second queen doesn't change because you did not pick, it was jack you picked first. So the event space for queen remains unchanged. And what's your event space for queen generally? Your event space for queen, you have 4 different queens. So the probability here will be 4 over 51. From 7 good and 3 bad items, 2 are drawn. From 7 good and 3 bad items, 2 are drawn. From 7 good and 3 bad items, 2 are drawn. We're leaving very soon, don't worry. I understand. You should understand I'm trying to seal this up. Just trust the process. From 7 good and 3 bad items, 2 are drawn. You have to find the probability that the second is bad, given that the first was bad. So from 7 good and 3 bad items, 2 are drawn. Find the probability that the second was bad, is bad, given that the first was bad. We must not leave here without the full conceiving of this topic. So from 7 good and 3 bad items, 2 are drawn. Find the probability that the second is bad, given that the first was bad. All right. So we have 7. We have good. We have 7. We have bad. We have 3. Sample space is 10. Obviously, the first was bad. You are removing 1 from the bad. You are left with 2. Of course, the sample space will reduce to 9. So this is 2/9. So let's take the last question for the night. Oh, sorry, 2 more questions, please. Just 2 more questions. A bag contains 5 red and 5 blue balls. A bag contains 5 red and 5 blue balls. Find probability that the second is red, given that the first was blue. A bag contains 5 red and 5 blue balls. Find probability that the second is red, given that the first was blue. Probability that the second was red, given that the first was blue. Of course, 5, 5, blue, red, right? Total sample 10. When you pick the first as blue, you are left with 9. You are left with 4 here, but you are picking red, so it's 5/9. Nobody is confused there, right? And the last but not the least for the night, from 7 red and 5 green balls, from 7 red and 5 green balls, 2 are drawn. Find the probability that the second is green, given that the first was green. All right. This is the last question for the night. 7 red and green, we have 5. We have to find the probability that the second was green, given that the first was green. All right. So if you look at this, it follows the same pattern, right? The sample space here, we have 7 plus 5. That will make a total of 12. Now, you drew the first as green. Of course, the green sample space reduces by 1. And the green event space, the sample space reduces by 11. So the total you have here for the second being green will be 4/11, because you are using, this is a tricky one because you pick green the first time, so you must subtract the first pick, which makes it 4/11. All right, so this is where we're going to stop for the night. It was very important we solidified our understanding of this, knowing fully well that it's always better to be good at what you know already. So guys, this is where we're stopping right now. We have other aspects of conditional probability we'll have to talk about in a subsequent class. Thank you very much for joining. Enjoy your night. Take care of yourself. Bye-bye.